So global stiffness matrix assembly. The global stiffness matrix is assembled by combining the stiffness matrices of all the elements. Each element contributes to the global matrix based on its node connections. In our case, for 2 elements and 3 nodes, the element 1 connects the node 10 and node 20, and element 2 connects node 20 and node 30. The global stiffness matrix K will be 6 by 6 matrix, means 2 degree of freedom per node, and we have 3 nodes. Each element's local stiffness matrix is formed into global coordinate system and added to the respective degree of freedom. So after applying the boundary conditions, so we can reduce the global stiffness matrix. Like at node 10, which is anchor, all degree of freedoms are fixed. It means dy at node 10 is equal to 0, and even rotation theta z at node 10 is equal to 0. So rows and columns corresponding to these degree of freedoms are eliminated, reducing the matrix sizes. Now the second thing is, after solving the displacements, so using the reduced global stiffness matrix K and applied load F, as we know that K, value of K as we calculated in the previous slide, and value of F we know that, so we can calculate the unknown value of X. So K is the stiffness matrix after boundary conditions, X is the displacement or rotation vector, which is we can say in our case is dy2 and theta z2, dy3 and theta z3, mean displacement and rotation at node 20 and displacement and rotation at node 30. So load vector, which is Fy in our case, we can say minus 1000 Newton at node 30. This is the force which is applying in downward direction, that's why it is in negative, and the reaction force against this, it will be in opposite direction, which will be 1000 Newton. The post solution calculations, after solving the displacement X, the Caesar calculates the internal forces and moments in each element. This is the first step Caesar normally does. After that, it calculates the stresses in pipe based on bending moment and axial force, and third thing, it calculates the reaction forces at node 10, which is anchor, that we discussed just before. Results from this example in Caesar 2, the displacement at node 10, it will be 0, rotation is 0 because it is fixed, mean anchor, node 10 is anchor, so no displacement, no rotation. Displacement at node 20, dy2 is minus 0.488 mm, and rotation is minus 0.173 radians, which is rotation at node 20, and vertical displacement at node 20. The displacement is in vertical downward, so that's why it is negative. So dy3 is minus 1.533 millimeter with vertical displacement at node 30, again in negative downward, and theta z3, which is minus 0.231 radian, again rotation at node 30. So after displacements, it calculates the reaction force at the node 10 and 20. So vertical reaction force Fy, this is the reaction force, right? That's why it is in positive. Actual force is downward, which is negative, and the reaction is upward, opposite to that, equal and opposite, right? So reaction will be in equal and in opposite direction, so it will be in positive 1000. So moment reactions mz1, again 10,000 Newton meter, which is again opposing the actual moment. So the key insights are, the displacement at node 20 and 30 reflects the flexibility of the pipe under the applied load at node 30. Reaction force at node 10 ensures the equilibrium in the system. These results are essential for evaluating the stresses and ensuring the code compliance. Mean to say, if the system is in equilibrium and it's not breaking, it means all the forces whatever is applied is in equilibrium, having an equal and opposite reaction forces or moments in the pipe. So maximum bending moment and stress calculation, if you see, the maximum bending occurs at node 10, which is far away from the applied location. So at node 10, element 1, m1 is 10,000 Newton meter. Bending moment is maximum due to the distance from the applied load. At node 20, element 1, so node 20, m2 moment, which is half of the m1 because the distance is half, So that's why the moment is half. At node 30, which is element 2, the moment is 0 because the distance from the applied load is equal to 0. So let's calculate the maximum bending stress using the bending stress formula. Is sigma b is equal to m over I into y, and in part 2 we already discussed this formula from the beam theory. Okay. So mx in our case is 10,000 Newton meter. Y is the distance from the neutral axis to the outer dia or outer edge of the pipe, so which is again OD divided by 2.1 meter, and I is the again the moment of inertia of the pipe, 2.7 Newton to the power minus 5, which we already calculated. So sigma b, after substituting the values in this formula, so sigma b is equal to 3.7 into 10 to the raised power 7 or 37 megapascal. So what it shows? It shows the bending stress is 37 megapascal, which must be compared to the allowable stress for the pipe material. In our case is steel, right? Carbon steel. If sigma b exceeds the allowable stresses, the design change such as increase in pipe thickness or adding the supports may be required. Third thing, the bending moment distribution confirms that node 10 experience the highest stress and deformation. So let's continue. Shear force and shear stress calculation. So after that, if we'll calculate the shear force and shear stress in our given example, so shear force at node 20, V shear is 7.288 into 10 to the power minus 12, which is again negligible due to the boundary condition and equilibrium. Mean to say, in our case at node 20, the force is applied in vertically downward, so that's why the shear force is negligible. So after calculating the shear force, we can calculate the shear stress, which is tau is equal to T into 16 dO over pi dO outer raised to power 4 minus d inner raised to power 4. So after substituting the shear stress, tau is equal to 1.22 into 10 to raised power minus 9 PA. Extremely small and insignificant compared to the bending stress. So in our case, bending stress is the governing stress, you can say. And if we'll combine the stress and the von Mises equations, sigma v is equal to square root of sigma b square plus 3 tau square, the whole under root. It comes out at 37 MPa because these values are negligible, very small. So just ignore this, and this come out as 37 MPa. So in our case, the von Mises stress is dominated by the bending stress in our case. So safety factor, if we'll calculate SF, so sigma allowable divided by sigma combined is equal to 250 MPa, which is the allowable value for the carbon steel, divided by 37, it comes out as 6.75. So what it tells us, the safety factor is above 1, indicating that the design is safe under the given loading condition. One thing. Second, if it is less than 1, then we have to improve the safety. And what are those options? Either we can increase the pipe thickness. Second, we can reduce the applied load. Third, we can add an additional support to distribute the load. So let's discuss in further slides the detail. When we will increase the thickness, what will be the impact? When we will reduce the load, what will be the impact? And when we will add the support, what will happen in our actual scenario? Solution and redesigning the system to improve the safety. To increase the safety factor to an acceptable level, which is typically 1.5, it is a ratio actually allowable to the calculated one, so it should be 1.5 times minimum. If it is beyond that, then the safety factor is more. If it is less than 1, it means this system is not safe. So we can explore the redesigning options. The first one, increase pipe wall thickness. Increasing the wall thickness increases the pipe's moment of inertia, which is I, that we already calculated in our previous slides, which will reduce the bending stress. Second, add intermediate support. If we'll add an intermediate support at point, which is in our case is node 20, midpoint of the pipe, it divides the span into two smaller spans, which reduces the bending moment significantly. Third is reduce the applied load. If the applied load at node 30 is reduced from 1000 Newton to less amount, the resulting stresses and displacement will decrease proportionally. The fourth one is use a higher strength material. Switching to material with a higher allowable stress, such as higher grade steel with allowable values equal to 450 megapascal, would improve the safety without changing the geometry. But before applying all these solutions, we need to check the economy and economical solution we need to propose. If we will change the material of the pipe, it's a costly solution. Similarly, if we'll change the thickness of the pipe, it will again have an impact on the cost, but adding an additional support, it will be a cheaper solution. So whenever we are proposing any solution or any modification, the solution should be economical solution. Advantages of using 1D beam element in Caesar software. The use of 1D beam element in Caesar for piping stress analysis offers several significant advantages, particularly in terms of efficiency and practicality. Here on the screen you can see few. First one is computational efficiency. It reduces the complexity, like beam elements simplify the mathematical representation of a 3D structure into 1D, requiring fewer degree of freedom compared to 2D or 3D finite element. Secondly, faster analysis. Since fewer nodes and elements are needed, the computational time and resources required for analysis are significantly reduced. So first benefit is simplified the model, reduces the computational efforts compared to 3D FEA analysis. Second is the simplicity in modeling. This methodology simplifies complex system into manageable component while providing accurate results for global stresses and displacement in the pipe. Secondly, straightforward geometry. The beam elements are ideal for representing the straight segment of the pipe, which dominate most piping system. Third is easy of input. The modeling process is user-friendly with less need of complex meshing or detailed geometric creation like we are doing in 3D FEA analysis. Third is adequate for global stress analysis. For most piping application, especially for global stresses and flexibility analysis, system level behavior, beam element effectively capture global deformation, forces and moments in the piping system, which are critical for evaluating compliance with industrial code like ASME B31.3, ASME B31.4, ASME B31.8, like that. Second, the thermal and pressure effect. They can handle thermal expansion, pressure loads and weight effectively. So this is the third advantage. Fourth one is incorporation of code-based parameters like the stress intensification factor, which is we normally call SIFs. The Caesar integrates SIFs and flexibility factor into the beam element analysis and provides a practical approximation for local stress concentrations. We can say the direct integration of the codes, stress checks, allowable limits are available in Caesar software. Fifth one is ability to model large and complex system. The modeling pipe as 1D beam element simplifies the analysis by focusing on structural behavior of the pipe system under various load such as weight, pressure, thermal expansion and dynamic forces. Scalability. The beam element allows the analysis of extensive pipe network which would be computationally infeasible using higher dimensional elements. Third is connection modeling. The beam element handle connections like T's, elbows and reducers efficiently with minimum manual input. Suitable for elastic analysis. The beam elements are well suited for linear elastic analysis, which is sufficient for most piping system under normal operating conditions. 7 is sport dynamic analysis. The model and harmonic analysis in the beam element can model systems vibration, natural frequencies and responses to harmonic load effectively. Second, simplified dynamic loads. They are efficient for evaluating dynamic effects such as water hammer or seismic loads. Number 8, integration with piping components. Beam elements can represent the interaction of pipe with supports, restraints and anchor accurately. Second is load distribution. They account for distributed load like insulation weight or fluid content efficiently. 9, cost effective for initial design. Quick assessment. Beam element allows rapid evaluation of various piping layouts during the initial design phase. Optimization. Changes in the design can be analyzed quickly to identify the best configuration at the initial phase of the project. 10th, the compatibility with the industry. So widely acceptable approach. The beam element method aligned with the traditional piping design practices, making it familiar to the engineer. Secondly, validation. The results from 1D beam models are well established and validated for most practical piping applications. So in short, we can say that while 1D beam elements have limitations like inability to capture the localized effect, but they are ideal for the majority of piping stress analysis tasks, providing a balance between the accuracy and efficiency.